Welcome to this lecture on the topic of braking of three-phase induction motor. In the previous lecture, we have seen the different methods used to control the speed of a three-phase induction motor. In this lecture, we will discuss the three main methods used for braking a three-phase induction motor. These methods are plugging or counter current braking, dynamic braking or rheostatic braking, and regenerative braking. Now, as induction motors are used for a wide range of application, and for some of these application, the induction motor may be required to stop within a specified time. So it is important to apply brakes and bring the motor to standstill as and when required. The simplest way to stop the induction motor is to disconnect it from the supply mains. The torque will no longer get developed, and the combined effect of the rotor and the external load will bring the motor to standstill. But sometimes, when rapid action is needed to stop the motor, mechanical braking, electrical braking, or a combination of both mechanical braking and electrical braking can be employed. Now, electric braking or electrical braking provides a precise control of the stopping moment and a smooth operation. So, for application which require a smooth and precise braking, electrical braking is generally preferred over mechanical braking. The three main methods of electrical braking are plugging, dynamic braking, and regenerative braking. So, let us first see plugging. In an induction motor, plugging can be achieved by changing the phase sequence of the motor. The phase sequence can be changed by interchanging the connections of any two phases of the stator with respect to the supply terminals. If we assume that during motoring action, the rotating magnetic field is rotating in clockwise direction, which also means the rotor is also rotating in clockwise direction. Now, after changing the phase sequence or interchanging the supply terminals of the stator, the new rotating magnetic field will reverse in direction and rotate in anti-clockwise direction. Now we know for a three-phase induction motor, the torque is developed in the same direction as the rotating magnetic field. Hence, the torque developed during plugging is in opposite direction to the torque developed during normal motoring operation. The change in the direction of the magnetic flux causes the electromagnetic torque to reverse its direction. But due to inertia, the rotor continues to rotate in clockwise direction. Thus, electromagnetic torque is in anticlockwise direction and the rotor is rotating in clockwise direction. So, the motor starts to decelerate, it slows down and will soon come to a standstill position. We have to remember that at the instant the speed of the motor becomes zero, the stator supply terminals must be disconnected and mechanical brakes must be applied. Otherwise, the rotor will start rotating in anti-clockwise direction. Figure shows the torque slip characteristics of a three-phase induction motor during motoring action, braking action, and generating action. As you can tell from the figure, for slip greater than 1, the rotating magnetic field reverses and the direction of torque is also opposite to that in motoring mode. So, the region of the curve for which slip is greater than 1 is called braking region. There are also certain problems associated with plugging. As during plugging, the stator field reverses and now the stator field and the rotor are rotating in opposite direction, so the slip suddenly increases from a small percentage to almost 200%. This is shown by the equation of the slip during plugging, and it comes as slip during plugging, that is SP is equals to 2 minus S where AC slip during normal motoring operation. Because of this high slip, firstly, the rotor induced voltages will increase by a large amount and the winding must be provided with additional insulation to withstand this high voltage. Secondly, there will be a large inrush of stator current, and thirdly, a very low power factor because high slip causes high rotor reactance. During plugging, the motor acts as a brake and absorbs the kinetic energy from the still revolving load, causing its speed to fall. This associated power Pm is dissipated as heat in the rotor. At the same time, the rotor also continues to draw power from the stator, which is also dissipated as heat. Thus, the heat developed in the rotor during braking period is very high. Hence, during plugging, a large amount of energy is wasted in the rotor as heat. Next, we will discuss about dynamic braking. Dynamic braking for a three-phase induction motor can be achieved by disconnecting the stator winding from the AC supply and exciting it from a separate DC source. Since a DC source is used for excitation, this method is also known as DC dynamic braking. The instant when the AC supply is disconnected and DC source is introduced across the terminal, there is no rotating magnetic field in the stator and it is replaced by a stationary magnetic field. But as the rotor is still in motion, it cuts the stationary magnetic field and a dynamic induced EMF is induced in the rotor conductors and a torque is produced but in opposite direction to the rotation of the rotor. This causes the motor to slow down and finally come to standstill. The advantage of dynamic braking over plugging is the absence of the reverse rotating magnetic field. So there is no tendency to run in backward direction after reaching zero speed, which was the case in case of plugging, where you have to disconnect the AC supply and apply mechanical brakes. So here, during dynamic braking, this problem of the motor running in backwards direction is not there, because when zero speed is received, there will be no EMF induced in the rotor and the opposite torque or backward torque to that of motoring mode will also be zero. Now this figure shows two different types of arrangement for employing DC dynamic braking. In figure A separate DC supply is available. A separate DC supply is available. In figure B, a rectifier is used to rectify the AC supply and give the required DC source for plugging. Next, we will discuss about regenerative braking. Now, regenerative braking for a three-phase induction motor can be achieved by running the motor above synchronous speed. When the induction motor is run above synchronous speed, the slip becomes negative. The rotor induced EMF reverses and a negative torque is produced. If the synchronous speed is brought down to a value such that Ns is less than Nr, Nr is the speed of the induction motor, the induction motor will start to operate as a generator and the stored kinetic energy at the shaft of the motor is extracted and is delivered as electrical energy to the AC supply source. The inertia of the moving load is used to convert the mechanical energy into electrical energy and is fed back into the power supply source. As we know, Ns is equals to 120 F by P. So the synchronous speed can be reduced either by switching over to a low frequency supply or by using a stator winding with larger number of poles for squirrel cage induction motor. Regenerative braking has the disadvantage of possibility of braking only at supersynchronous speeds or speeds above synchronous speeds for fixed frequency supplies. A typical application of regenerative braking is its use in electrical traction systems such as trains or trams. There are often thousands of tons on the move, and this constitutes considerable inertia. If this energy can be transformed into electrical energy and simultaneously it slows down the train or tram, a large saving in electricity costs can be achieved. There will also be saving in the wear and tear on the brake shoes used in the mechanical system. Thank you. I hope this lecture will help you in understanding the different braking methods which are employed in for braking a three-phase induction motor.